this is quite a different sort of thing. We remember that in the first place, that we were very interested in Hadamard matrices because of properties that they have, which were very good for signal processing. So they were especially good for, error correction codes, for looking at transformations from one sort of device to another, and for compression and various other reasons. But we've always, when we talk about Hadamard matrices, we always quote that the elements are on the unit disk and have modulus less than or equal to 1. But when we think of Hadamard matrices, they're always integer. Now, there's an application has come up in the design of aircraft, metals for aircraft. So, and the design needs to have matrices which have modulus less than, every element modulus less than or equal to 1, and be orthogonal, but they don't have to be integer. They can be real. So this is the switch away from the totally discrete into the space of real things. Now, when you come to do that, that's what we call a Cretan matrix. A Cretan matrix is a matrix which is orthogonal. It has one element in each row, at least one, and the other elements have got to have modulus less than or equal to 1. And so we're looking for these things. Now, my colleague that works on it from Russia has been looking at it totally from a numerical point of view. He has developed a computer program, which will find these matrices very accurately, but he didn't know of anything which was like it from our side of the fence, talking about Hadamard matrices. So he wrote a paper about Hadamard matrices of order 3 and 5, and you would say, what? There's no matrices of order 3 and 5. But after we had a long discussion of philosophy, we decided that's because of the notation we've used. Now, what I've got in this little paper is some example we made of the Cretan matrix. Now, Cretan matrix has levels. Hadamard matrix has levels too, but it only has 2 levels, 1 and -1. A conference matrix will have 3 levels, 0, 1 and -1, and it's still orthogonal, still satisfies everything is orthogonal. The elements are all less than or equal to modulus less than or equal to 1. And so it is also one of these Cretan matrices. But we wanted to see if we could get other Cretan matrices which had the correct properties, but the levels could be quite different. So that, yes. So what we're doing is we're looking at these matrices. Yep. And what we've got is we're going to show that every Hadamard matrix is equivalent to the coexistence of a Cretan matrix with 2 levels. And we'll just do a small example of that so we can see how it's going. Yes, can we move it down, or can I move it down? Okay.
I think you can
now,
move it.
The thing we have to remember is that we want the determinant to be maximal. And what we're going to do is we're going to say we want this matrix to be such that it has a border, and those are those sigma elements there, border on both sides. It has a core, which we call B, and it has another element up here, which is X. And we don't know what that is at the moment. Now, we only refer to as Cretan matrices, which we're going to show how we can make them. If we can move that down, can I move that up? Yeah. Okay. Now, when we look at the determinants, maximal determinant, you see that Barber showed that if you have elements with entries that have a modulus less than or equal to 1 of order n, any n, then you've got the determinant is bounded by this amount, and or asymptotically, that's 0.85. So it's not terribly huge, but it's not terribly small either. Then Wojos showed that if you have things which are congruent to 2 mod 4, then you got this bound. So we do know some bounds of these things, even though they don't have elements plus or minus 1. Pull it down a bit. Yep, down a bit. Okay. Now, we've got to emphasize this. In general, a Cretan matrix of order n, which has Tor levels, they're made from orthogonal matrices where we replace the variables by appropriate real numbers with modulus less than or equal to 1. And the least one entry in each row and column is 1. We'll go down a bit. Okay. All right. Now, of course, for this audience, I don't have to go into this. We have what is an SBIBD. We know that the incidence matrix of an SBIBD can always be found by looking at the intersection of the rows and columns. And for every SBIBD, there is complementary SBID, where the incidence matrix, we swap the zeros and ones. Now, there is a mistake in this typing. Is a G here. That should be another right bracket to match this one. So it's not really wrong. It's just not very clear. Okay. So we use this little combinatorial trick, and we can look at these because we've got these equations that A and B, or A and B, and we can write down the determinant. So that's easy to do. Okay, now let's move down a bit so we can get this part here. Okay, now the variables we're going to have this matrix SS transpose or S transpose S is going to be W times the identity matrix. It doesn't have to be N. N is what we're talking about with Hadamard matrices, but we're going to have a W. And this has got two types of equations which come from looking at the inner products of the row and columns. First of all, the inner product of a row itself will give us the omega, which has got to be constant. And we call that the radius. And then there's the equations which come from taking the inner products of distinct rows, and we look at those, and they've got to be each got to be orthogonal to other, and they arise from the inner products, and we call this a characteristic equation or equations. So we can say that we have an orthogonal equation. Now, an example, come down here, oh, there. This is an example of a small design Cretan matrix. It's got two kinds of levels. It's got the level X and it's got the level Y. Now, how do we find out about this more? We'll go down. Now, okay. Because it's orthogonal, we're going to have x squared plus 4y squared is equal to omega, the weight. For the inner products things, we're going to have these equations as equal to naught. And to make it Cretan, we're going to force x to be 1. Since we've got to have a 1 in each row and column, we choose x to be 1. Now, this means that the characteristic equation can be solved, and it gives y minus 2/3, which means omega is going to be 3 1/3. The determinant of this is 20.28. So we say it's a Cretan, order 5, 2 levels with radius 10^3 and determinant this number here. So we have got a determinant and we have got a matrix which is orthogonal of order 5, but it's not a Hadamard matrix. It's what we now call a Cretan matrix. Now, all of this stuff here is because in the Russian literature, these things have already got names, and just want to make it clear that you could switch from one to the other. So the name for the Hadamard Mersenne numbers is the Cretan 4t-1. He calls them Mersenne numbers, Mersenne matrices. Now, the mathematical will go down, please. Okay. We remember that actually the idea of the SBIBDs and Hadamard matrices was done by J.A. Todd, and it's in the same paper as Ray, same journal copy as Paley's things. So we're going to look at this SBIBD and it's complementary. And they can be written with incidence matrices and they're still complementary, and we can permute them and find lots of other things. Down, please. Okay. So this would be what the SBIBD says. But the one is the complement of the other. Now, we can replace them by the zeros by x's, or in the ones by y, or the other way around. And this would be the SBIBD 2. And down, please. And that would be the other one. Now, if we want to turn this into a Cretan matrix, we're going to have some element is 1. So without loss of generality, we're going to say that x is 1. And the characteristic equation, which we get from taking the inner product of these equations here, there's xy, 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 4xy, and x squared and y squared. So we've got 4x squared plus 3y squared for each one of those by itself. And for the other, across here, we've got this equation. Now, that means this is going to be a Cretan matrix of order 7 and with 2 levels. To solve it, we solve these equations, and what we get is that y is going to be minus 2 plus root 2, and the radius is going to be 4x squared plus 3y squared, which is about 5.02 in this case. Yes, please come down. And that's, yeah, we could, we've noticed that the 7.2 lambda 4t 1 2t has got the determinant 3.343, and the other two is smaller. So why we want to say that was easy. That was very easy to make, very easy to find. And what we're doing is now searching for more. Now, this thing here it allows us to always have the determinant, and it's a maximum determinant, but it's a quite slightly different problem. Remember, in that we're not restricted to having 2 levels. We can have any number of levels, and any of them can be real numbers. Please. So it looks, you can see the pattern in there. Anybody who loves SBIBDs will see the pattern in there from the SBIBD and this complement. Now, this is very easy to prove. Let's go down, please. First thing we want to do is we've specified it. So if we get Cretan matrices from the SBIBD theorem, then whenever we have an SBIBD, we've got a 2-level Cretan matrix, which can be written as V 2 levels. And then here is from the VK lambda with the X's and Y's, and then the determinant. I haven't put it in there, but I've just written determinant to let it be. And these are the 2 variables we got. Now, we notice in all the Cretan Hadamard cases, but not all of them, this Cretan matrix gives the higher determinant. This one gives a lower determinant. I don't know why that should happen, but it does. Well, of course, then we say, we know that the Hadamard matrix is equivalent to the SBIBD. That's from the time of Todd and Paley in 1933, so it's not exactly new. Down, please. Now, we've got this lemma up here. We've just said, we've shown that we can go from an SBIBD to a Cretan matrix. And so we've always got from the SBIBD to the Cretan matrix. Now, what we can do with that is we can actually choose the X and the Y in general, and we will be able to give the formula for a Cretan matrix made from the SBIBDs. Down, please. So, in fact, we end up with an equation like this, with the product of the rows of I and J as that. So we've got, it satisfies the orthogonality equation because of this 0. Now, the Cretan to Hadamard is just that whenever there is an SBIBD, this Hadamard matrix. So, in fact, with the coexistence of Hadamard matrices and Cretan Mersenne matrices is very, very straightforward. And it could be given as an exercise in algebra or combinatorics to any of our students. Down, please. Now, so that means we have a conjecture. Since all Hadamard matrices are conjectured to exist for orders 4t, and an integer 2-level Cretan Mersenne matrices are conjectured to exist for all orders 4t minus 1, t greater than 0 an integer. Now, there's quite a lot of questions we need to ask. We're a very new area of study because those that have been found in the past have always been found by a numerical algorithm and searching on a computer. What we need to know is, what is the minimum number of variables that can be used? Well, obviously 2, it looks like 2. What are the determinants that can be found for these Cretan matrices? Why do the congruence classes of the orders make such a difference to the proliferation of Cretan matrices for a given order? We want to find the Cretan matrix with maximum and minimum determinant for a given order. can one be found with fewer levels? And we conjecture that if omega is approximately equal to V, we will get some unusual conditions. I think we're just about at the end, aren't we? Let me just see. Yes. So I wanted to bring this to your attention because I think it's important that we know that there are other people looking at problems which are related to our interest in orthogonal matrices and Hadamard matrices, but which are being approached from a totally different direction. And I thank you very much for listening to me.